Hi, welcome back to the fifth session of the chapter 2. I'm Ishan Desai, your physics tutor. Now, students, here in this today's session, we will be discussing, the term potential energy. We'll start with the single point charge system, and then later we will also derive an equation for n number of point charge system. So we'll also try to obtain the equation when the same point charge system will be placed in some external electric field. And then later, finally, we'll be also discussing the potential energy of an electric dipole when it will be placed in some external field. Along with some special cases, we'll have some discussion. So students, these are the topics that we're going to see here in this, the today's class, right? And of course, some numericals will be taken, right? So students, let us quickly begin with the very first topic of the today's session. We'll see that. Now, since when you talk about electric potential energy, we know that it's the energy possessed by the system of charges due to the change happening in the positioning of those charges, right? When you're having two like charges which are separated by an infinite distance apart, right? Here in this case, the potential energy is zero because the work done in moving that charge, okay, which is at an infinite distance from the other, right, charge is going to be a zero. Now, when you want to bring them closer, guys, in that case, we have to do some work against the repulsive force between these two like charges, right? And we are talking about a conservative force here, right? So whatever work you're going to do here in this case will be getting stored in the form of potential energy. Now, here, students, we will be discussing about the potential energy of, 2-point charge system, the 3-point charge system, as well as we will try to obtain equation in general for a n-point charge system. Well, now since let us begin with the 2-point charge system. Okay, let us say that you are having a 2-point charges, okay, a like charges at somewhere at infinity. Okay, and here I'm having a space where I don't have any electric field, okay, no external field, let me just say, right? Now, I'll be bringing one of the charge which is at infinity, okay, to this particular point somewhere here in the space, okay. So let me just bring that Q1 charge from infinity to this particular point P here in the space, okay. And let me just say that this charge Q1 is at some position vector of R1 from the origin. This is just to, as for a reference, I'm just, choosing this, the position vector, okay. Now, students, will there be any work done in moving this charge? Do you think? No, right? Why, students? Because there's no external field against which I'm going to do a work, right? So if there is no external field, the work that we're going to do here in moving this, the charge Q1 from infinity to this particular point is going to be a zero, right? So that is the first thing that we know here. Now, let me bring the another charge, okay, but before bringing that, the another charge Q2 somewhere here at a point 2, okay, let us discuss about this point charge Q1 first, okay. Since we have brought it and placed it over here, I know that, students, there will be an electric field due to this positive charge Q1, right? And I can easily find out the electric potential also with the help of this relation that I know. When you're having a point charge, the potential at any point in the surrounding space is 1/4 pi epsilon naught, the charge Q1 over the distance at which you choose your point. So let me just say here it is going to be a R1P. P is any general point here in the space, right? So this is what we know. Now, if I want to bring that charge Q2 from infinity, okay, to this particular point here, okay, at the position vector of students R2 from the origin, right, I have to do some work, right? Because, students, now we are bringing the charge Q2 in some field, right? And that field is created due to this, the charge Q1 here in this case. And if you remember, students, the definition of an electric potential, we know that whenever you do a work in moving a unit positive charge from infinity to that particular point against electrostatic force, that will be giving you the electric potential at that particular point. So this is a relation that we are having here, and just rearranging that, I can easily find out the work done in moving this charge Q2 right from infinity to that particular point here. Yeah, so work done will be equal to potential here in this case, that V is due to this charge Q1, right, into the charge Q2, I can say, right? And let us say the distance of separation between them is a R12 here in this case. So if you just see this relation, what I can write it something like this: the work done W2 here in this case in moving the charge Q2 will be 1 upon 4 pi epsilon naught. Yes, the charge, the Q1 over the distance, okay, that is R12 into the Q2 in the numerator. So this is what the work done I'm having here. Now we are talking about this 2 point charge system, right? So what is the overall work done here in bringing these 2 point charges here at this points, right? So it is W will be equal to W1 plus W2. W1 here I know it's 0, right? And W2 just now we have calculated, and this is what the relation will look like. Now we know that students, whenever you do a work, okay, against a conservative force, that will be stored in the form of potential energy. So this W I can replace it by a U cap, right? So that is nothing but a potential energy. So this is a potential energy for a 2 point charge system. Now students, let us bring another third charge now, okay, and let us see how the relation looks like. Okay, but before that students, let me just again make some points here. Okay, if you just see, the potential energy that we are getting here is positive because we have taken here both these point charges to be positive, right? If I had taken let us say the one of the charge would have been a negative, in that case students, the potential energy would have been negative. So please make a note of it. Yeah, and again students, whether you're bringing that first, here what I have done here, I have brought my Q1 here first and later I have brought my Q2, right? So if you bring a Q2 first and Q1 later, right, so the equation remains the same. Okay, so the equation here, it doesn't depend upon whether you are taking which charge here first. It just depends upon the present charge configuration. Okay, whatever you are having, whatever you're seeing, it depends on that. Okay, not whether you are taking a which charge first. No, the relation will be same. Now let us get a third charge. I'm again getting the third charge right from infinity. Let us say I'm just placing it at here a 0.3, right? So here this time I have to do a work against the electrostatic force that will be due to this charge Q1 as well as due to a charge Q2, or else I know at this 0.3 students, the potential at a 0.3, right, will be due to the charge Q1 as well as due to charge Q2, right? So here in this case, that W3, okay, the work done in moving the charge 3 will be students, the potential at the 0.3 due to the charge Q1 into the charge Q3 that I know. Yeah, and as well as plus the potential at that 0.3 due to the charge Q2 into the charge Q3 here, right? And let us say here the R1, I can say that R13 let be the distance of separation between these two charges Q1 and Q3, as well as R23 be the distance of separation between these two charges, that is Q2 and Q3. And here in this case students, I know already the potential. Here I can just substitute it there. So W3 will be equal to 1 upon 4 pi epsilon naught, the charge Q1 over the R13 into the Q3, plus 1 upon 4 pi epsilon naught, the charge Q2 over the R23 into the charge Q3. And this is what I'm having here. Now for this 3 charge system, right, I can say that students, the overall work done will be equal to W1 plus W2 plus W3 this time, right? And this is what I'm having here, right? So if you just see students, again I can replace that work done by potential energy, and this is how I can write it down here in this case. So this is the potential energy when you're having a 3 charge system, okay, 3 point charges system. Now what if students, when you're having an n number of point charges, right? In such a case, how to get a general relation? So if you just see here for a n point charge system, I can write this potential energy to be as half 1 upon 4 pi epsilon naught. Okay, I'll be making use of a double summation here. Summation I is equal to 1 going to n, and summation j is equal to 1 going to n, where I should not be equal to a j, and qij upon rij, right? So if you just see students here, right, why that half is coming here into the picture, right? Because we are making a use of a double summation. Okay, double summation will give me 2 pairs okay, every time. Because if you just see for a 3-point charge system, inside the bracket we're having q1 into q2 upon r12 plus q1 into q3 upon r13 plus q2 into q3 upon r23, right? So these are what we are having here, right? So if I just simply make a use of a double summation, okay, I'll be getting that q1 q2 upon r12, I'll be getting plus I'll be getting q2 into q1 upon r21, which is the same as that, right? So if I just simply use a double summation, right? So double summation gives you the double pair, okay? So in order to in order to just compensate for that, we have to take it a half here. So that will take care about that whatever the double pair you'll be getting when you take a double summation. Okay, so that is why you'll be introducing a factor of half here in this case. So since this is the relation that we are having when you're having an endpoint charge system, right? Well, now we will be moving forward. We will be discussing about the potential energy of a charge when it is placed in an external field. We'll see that. Now here I'm having this external field where I'm going to place my charges and I'm going to obtain the electrical potential energy of those charges at that particular point. Now, before I move those charges, students, I'll be making one assumption. The charges that I'm going to consider here will be very small, okay, such that no influence of those charges is there on the external source charge, which is creating this external field. Okay, and even students, if suppose we are considering some finite charges, okay, the influence of those charges can be ignored, provided the external source charge is creating a strong electric field. So this is what we consider here. Now, if I want to move the charge q, okay, from infinity to a particular point at a position vector of some r1, r, let us say, from the origin, right? I have to do some work, right? And a work done in moving this charge q from infinity to a position vector of r1 from the origin, which I can write it to be as w will be equal to, students, it will be a charge q into the the external electric potential at this particular point, right? This is what we are having here, if you just see. And the w I can replace it by a u, that will give me a, because I know work done will be getting stored in the form potential energy, so u will be equal to, students, the charge q into the electric potential. Okay, so here if you just see, students, this is a relation that we are having here. Now if I just say, students, if you're having an electron, okay, of charge 1.6 into 10 to the power minus 19 coulomb, right? And if you're moving that electron across a potential difference of 1 volt, right? So what will be the change in potential energy that we'll be getting? It is 1.6 into 10 to the power minus 19 joules, right? And in atomic physics, students, we also take that the unit as a electrovolt, right? So what is the 1 electrovolt, students? I'll say it's nothing but the change in potential energy, okay, or else the gain or else the lost in a potential energy by an electron when it moves across a potential difference of 1 volt. So this is how I can define the electrovolt. Now, students, if suppose this is for a single point charge, I have moved into the the external field, right? Suppose if I want to bring another the charge q2 from, let us say, infinity to some position vector of r2 from the origin, right? So here in this case, students, I have to do some work in moving that q2 charge as well, right? So here in this case, students, if you just see the work done in moving this q2 charge from infinity, right, to this point, which is at a position vector of r2, right, will be, students, w2 here in this case. I can say it is going to be a charge q2 into the external electric potential at that particular point. Yes, plus, students, I also have to, plus it is going to be a, students, I can say we have to also do a work, due to this, the charge q1 that we have taken here, right? Because both are positive charges, so there will be a repulsive force between them as well. So I have to do a work here, positive here in this case. So if you just see, it is going to be a, students, the charge q2 into the electric potential at that point 2 due to the charge q1. So this is, again, I can write it here in this case, and this is the final relation that we are getting here for a potential energy when you're having a 2 charge system in an external field. So this is the equation that we are having here. Now, moving forward, students, we will be discussing about the electrical potential energy for a dipole when it is placed in an external field. Now here, this is an electric dipole which is placed in some external electric field. And since I know that on this positive charge, there will be a force exerting, which is going to be a Q times vector E. And on this negative charge, it is going to be here in this direction, minus Q vector E. And if you just see this, both the forces, right, will be forming a couple, right? Now, students, when I said a couple, right, the net force that is exerting on this, the dipole is going to be a 0. Right? But the dipole is going to experience some torque here in this case. Now the torque that is created here on this dipole, will make this dipole going in a clockwise direction, right? Now here, students, what I will be doing is that, let us say if I bring some external torque, okay, such that, it's going to neutralize the torque which is already exiting on this dipole, which means, students, I will be trying to move this the dipole anti-clockwise direction, such that the torque that will be created on this, the external torque, will be opposite to the torque which is already creating on this dipole. Now, students, one assumption I will be making here, right, when I will be moving this dipole in an anti-clockwise direction, right, the angular speed that I'm going to consider here is going to be a very, very small, such that there is no angular acceleration of this dipole. So that is the assumption I make here. That means, students, the external torque that I'm going to exit on this dipole will be same as the torque which is already exiting on this dipole, right? So if you remember the formula, guys, to find out the torque, right, the torque is nothing but the magnitude of the force that is exiting here, and the students, into the perpendicular distance between the two separating forces here, right? So this is the formula that we know, right? So what is the force, right? We know the force, that is Q times E, right, the magnitude of that. So we have to find out the perpendicular distance between these two separating forces, right? So if you just see, I'm having here triangle forming, this is the angle theta, right? Let us say the dipole moment is forming some angle theta with the electric field, right? So this is a perpendicular side of my triangle, this is a hypotenuse side, which is a 2a, right? And if you just see, students, we can use a trigonometric identity, that is sine theta is opposite upon a hypotenuse, right? Yeah, so we need an opposite side. So over here, students, the opposite side will be the hypotenuse side, that is 2a into the sine theta. So this is going to be a 2a sine theta, right? That's the opposite side. So when I substitute there, the torque will be equal to Q times the E into 2a sine theta. And if you remember, students, what is an electric dipole moment? Yes, which we represent by P, that is nothing but Q times the 2a, right? So I can just replace that Q into 2a by P, and the torque here I will be getting is the electric dipole moment into the electric field into sine theta. So this is what I'm having here. Now, students, let us say you are applying that external torque on this the electric dipole, right? And you are going to basically move this in an anti-clockwise direction, right? So let us say you're moving this electric dipole by a small angle of d theta, okay? Yes, in an anti-clockwise direction. This is that d theta here, right? So here, if we just see, we are doing a small amount of work, right? And that small work, if you just see, dw will be equal to a tau into d theta. That's a small angular displacement that we are making here, right? So this is a small work that we can calculate. Now let us say, if you are moving this electric dipole, let us say at the starting, the electric dipole moment is making some angle of theta 1 with the electric field, and you are taking it to some other angle of theta 2, right? So here in this case, students, we can integrate it and we can get overall work done, right? So the total work done will be equal to an integral of, okay, tau d theta, and the limits will be from theta 1 to theta 2. Right? And students, when I substitute the tau here, which we have already calculated, right? So the total work done will be equal to integral of the tau is p e sine theta d theta, limits again remains the same. So over that, electric dipole moment and the electric field is a constant, so I can take them out from there, and in the integration, if you just see, we will be having a sine theta d theta, right? So when I integrate the sine theta, students, What is the integration of sine theta? We know it's a minus cos theta, right? So this is the equation that we are having here. Then later, the next step, you have to substitute the upper limits and lower limits. So if you just see here in this case, inside the bracket, students, what we will be having here is a minus cos theta 2 minus, again, minus of cos theta 1. So you can just open it up again, multiplication, right? Minus into minus into positive. And I can rearrange it something like this. The total work done will be equal to PE, and it is going to be, students, cos theta 1 minus cos theta 2, right? Now, since we know that the work that we're going to do here in moving this dipole, right, will be getting stored in the form of potential energy, right? So that W, instead of W, I can write it by, a capital U, which is nothing but a potential energy, right? Potential energy of a dipole when it is placed in an external electric field is going to be, students, a dipole moment electric field into inside a bracket cos theta 1 minus cos theta 2. So this is the equation that we are having here, right? So you can make a note of it. Now let us say, students, okay, let us say if suppose the electric dipole moment was placed initially at some angle of theta 1. Okay, let us say angle of 90 degree. Okay, let us say that theta 1 is equal to some 90 degree with the electric field here, right? So in this case, students, right, and then later let us say from this angle of theta 1 we are moving it to some other angle of theta, right? So here the same equation that we are having here, right? So that theta 1 goes to 90, so cos of 90 gives you 0, right? And that theta 2, let us say I'm choosing it to some angle theta, let us say we are going, right? So that theta 2 I can replace it by theta, right? So what again I can write here, considering initially the dipole is placed at an angle of 90 degree with the electric field, I can say that the potential energy will be, students, minus PE cos theta, right? So this is what I will be getting an equation. So which again I can write in the form of dot product. So that will become minus vector P dot vector E. So you can also make a note of these two, equations. Like, and when we consider the theta 1 here is of 90 degree, right? Now we will be discussing about some special cases. So when the electric dipole moment is parallel to the electric field, right? Over here the angle between them is 0 degree. Cos of 0 gives you 1, right? And the potential energy that we'll be getting here is minus electric dipole moment into the electric field. So which tells me that the potential energy here, is going to be a minimum. So which is a case of, a stable equilibrium, right? Position of stable equilibrium. When the electric dipole moment will be a perpendicular to this, electric field, right? Here in this case, students, the cos of 90 gives you 0, and the potential energy of this dipole is going to be a 0, and this is a case of a 0 energy, right? So again, students, this can be very well explained. Let us say when you're having this electric dipole, right, somewhere at infinity, and you're trying to bring it from infinity in this particular at this particular point, let us say, right, in this external field, right? So the work that we're going to do here on this positive charge, right, by an external agent. So right now here the force that is exerting is an electrostatic force, and that is here in this direction, right? So I'm saying that the work done by an external agent in moving this positive charge from infinity to this particular point is going to be a positive, right? And a work done by the external agent in moving this negative charge, right, from infinity to this particular point is going to be a negative. So the net work done on this electric dipole is going to be a 0, right? Yes, so when the work done here is 0, the potential energy of the dipole has to be a 0, right? So that can be very well explained, in this way as well. Now, when the electric dipole moment is, let us say, anti-parallel to the electric field line, or else let us say it is an angle of 180 degree, right? In that case, cos of 180 degree gives you -1, and negative will be a positive, and the potential energy here will be a electric dipole moment into the electric field, right? So which tells me that there will be a maximum potential energy. So this is the case of position of, I'll say unstable, the equilibrium, right? So these are the 3 different cases, students, that we have discussed, right? So well, students, this is all about the potential energy of an electric dipole when it is placed in some external, the electric field. So now, students, the next that we're going to do here is some problem solving. So let us quickly begin with the first question of this today's class. Now here, if we just see the question, 4 charges are arranged at the corners of A, B, C, D of side D, as you can see here in this figure, right? And there are 2 parts of this question. The first part says, find the work required to put together this arrangement, right? The arrangement that you are having here, right? So let us go with the first part. So let me just take out a Q naught from here that is related to the second part of the question. So here, these are the charges A at a point A, B, C, and D. These are the charges that we are having here, and we have to find out the work required, right? So first of all, students, when you do a calculations of work, right, it just depends upon the final arrangement of the charges that you are having, right, and not which charge you have placed first or last, right? So here it's very simple calculation, students. If you just see here, let me just go here with the positive charge placed at point A. First of all, I know, students, the work required here in this case will be a 0, right? And then when I get another charge, negative charge at a point B, right, at a distance of some D from the charge which is located at a point A, right? So work done in bringing this negative charge at a point B, right, is nothing but, students, the charge that we're going to have here, right, that is the negative charge into the electric potential at a point B due to the charge which is at a point A, right? So here I can write my work done. The work done will be equal to, right, the negative charge that I'm having here, that is a negative Q, into the electric potential at that point, B. So that will be 1 upon, I can write 1 upon 4 pi epsilon naught, the charge, positive charge over the distance between them is of D. Okay, this is what we are having here. Now let me just get another charge here, a positive charge. I'm placing it at point C. So here the work done in bringing this positive charge at a point C is nothing but, students, the charge Q at a point C into the electric potential at this point C, okay, due to the charge which is placed at point A, as well as due to the charge which is placed at point B, right? So let me write it here, 1 upon 4 pi epsilon naught, that will be a constant here, okay, for here in this case as well. Let me just say here the distance of separation here in this case is D. So here it will be again, since minus Q into positive Q over the distance of separation is D. Now here, if you just see the distance between this A and C, this is my triangle forming here from the Pythagoras theorem. I can get this to be as a square root of a 2 times a D, right? So that's the hypotenuse side of my triangle, and here this will become, guys, positive Q into Q over the square root of 2 times a D. So this is what we are having now, right? Well, now since let us get another charge, okay, a negative charge. Let me just place it at a point D. Now here, students, the work done, if I want to calculate, right, it will be the charge which is at a point D into the electric potential at a point D due to the charge placed at point A, the charge placed at a point B, as well as the charge which is placed at a point C. So again, 1 upon 4 pi epsilon naught will be a constant. Let me just take it out there, right? And here in this case, if you just see, these are the distance of separation that we are having, right? So if I consider this, the charge which is placed at point C, so here this is going to be a negative Q into positive Q over the distance D. Then if I just consider this, the charge which is placed at a point B, again the hypotenuse side, so here this time it will be a minus Q into minus Q. That will become a positive Q into Q over, I can say it is going to be a square root of 2 times D. And finally here we are having a negative Q, positive Q, and a distance of separation is of D, right? So this is what we are having here. Now since from here, what I do here, let me just add one more step, 1 upon 4 pi epsilon naught, and I can just multiply that minus Q into Q. That will give you a minus Q square upon D. Here as well as, students, minus Q square upon D. This is going to be a plus Q square upon square root of 2 times D, minus Q square upon D, again plus Q square upon square root of 2 times D, minus Q square upon D. So this is what we have. Now from here, students, I can take that Q square upon D common out. Yeah, so let me just write it here. I can take that, minus, okay, along with that minus sign, I will be taking them out. So here in this case, or else let me just keep that minus as it is for now. So I'll just take it, the Q square out, Q square upon 4 pi epsilon naught times D, right? So what we will be having the first term will be a -1. Second term will be also -1 inside the bracket. The third term, it will be a 1 upon square root of 2. Fourth term, again a -1. Fifth term, 1 upon square root of 2. And again a sixth term, we will be having a -1. So this is what we have it here. Now, students, from here on, the things are very simpler. You can just say that q square upon 4 pi epsilon naught times d, right? And you just add it up. Here we are having total 4, -4. And when you add this up, the 1 upon square root of 2 plus 1 upon square root of 2, that will give us 2 upon square root of 2, right? So this is what we have. Now, students, from here, if you just see this 2 upon square root of 2, right? So which I can also write it. It's a very simple. Let me just do it here and show you. When you're having, students, 2 over the square root of 2, so that I can write it to be the 2 to the power half, right? So which I can also say that it is going to be a 2, and when it goes up, right, so that will be multiply 2 to the power minus half, and here we are having 1. So the power gets, you can just 1 minus half. So that will give me again 2 to the power half, which I can write it to be the square root of 2, right? So here, so the same thing I do here. Okay, let me just write it down here as q square upon, students, 4 pi epsilon naught times d, and here I will be having -4 plus square root of 2, right? So if you want, you can also rearrange this, and you can write it something like this. The work done will be, students, I can say negative, if I take it out, q square upon 4 pi epsilon naught times d, and inside the bracket we will be having a 4 minus a square root of 2. So this is the work done in making this arrangement of the charges at point A, B, C, D that we are having here, right? So that's the answer. Now, students, let us go for the second part. For the second part, if you just see, a charge Q0 is brought to the center E of the square. The 4 charges being held fixed at its corner. How much extra work is needed to do this, right? So if I bring a Q0 charge and if I place it at a point E, right? Now here, students, if you just see the work that we're going to do, extra work has been asked, right, in placing this Q0 charge. So here, the work that we will be doing here in this case, let us say the total extra work, okay, let us say the extra work, okay, that we will be doing in getting this Q0 charge, okay, at point A, right? So it will be a charge Q0 at a point E into the electric potential at a point E due to all the charges which are placed over here at a point A, at a point B, at a point C, as well as a point D, right? So if I do that, again here, if you just see, students, that 1 upon 4 pi epsilon naught, is going to be common out. Let me just take it out, right? So the charge Q0 that we are having here, and if I consider a charge which is placed at point A, that's a positive charge. So that is going to be a positive Q, and over the distance. Distance is what? We know, students, the hypotenuse side. We know this hypotenuse side, okay, between the A and C is a square root of 2 times the D. So if I'm interested in this distance between a A and a point E, that is what it is going to be, a square root of 2 times d by 2. I can write it, right? So here again, square root of 2 by 2. Students, if you just see here, again, I'll just show you here. So when you're having, students, a square root of 2 by 2, right, I can say that this 2, 1 over 2 into 2 to the power minus half, and that I can write it to be as, students, 1 upon square root of 2. This is how I can write it, right? This is 1 upon, let me just, I think that is a bit, yeah, so here it is, let me write it proper, yeah. So if you just see, students, here in this case, it will be, this is minus half, so that will give 1 upon square root of 2, like that also you can write, right? So what you are having here is square root of 2 times d by 2. You can also write it to be as d upon square root of 2, right? So let me write it here, d upon square root of 2, right? Again, same way, students, the charge which is at a point B, so you can find out here, that will be, students, minus Q0 into Q over, again, it is going to be a d upon square root of 2. Same way here, we are having plus Q0 into Q upon a d upon square root of 2, right? And then again, here we are having this charge at a point D, so that will give me a minus Q0 into Q over the d upon square root of 2. So if you just see, all these terms will be getting cancelled out, right? And what we will be having here, the extra work that is required to be as a 0 joules. right? So no work is required in placing that Q0 charge, right? So that comes out to be a 0. So that's the answer for this, the question, right? So well, now since we will be moving forward with the next question. Now this is the second question, which again has got 3 parts. So let us see the first part, which says determine the electrostatic potential energy of a system consisting of 2 charges, 7 microcoulomb and minus 2 microcoulomb with no external field, placed at minus 9 centimeter, 0, 0 and 9 centimeter, 0, 0 respectively, right? So since these are the 2 charges, one is a positive charge, other one is a negative charge, and these are their locations, right? Now, since here straight away we can find out the potential energy, right, with the help of this relation. The potential energy U is nothing but, I know that it will be a 1 upon 4 pi epsilon naught, the product of the 2 charges Q1 into Q2 over the distance between the 2 charges, right? Now here, what is this 1 upon 4 pi epsilon naught, right? Here, let me just write down first of all a given thing, right? We know the charge Q1, is of 7 microcoulomb, so which I can write it to be as a 7 into 10 to the power minus 6 coulomb, right? Since the microcoulomb. The charge Q2, same way, students, it's given to be as a minus 2 microcoulomb, which I can write it to be as a minus 2 into 10 to the power minus 6 coulomb, right? And there, students, 1 upon 4 pi epsilon naught, which is nothing but a K constant. And you guys know already the value of K. It is 9 into 10 to the power 9 Newton meter square per coulomb square, right? So that's the value you guys know. And students, here the D is required. So the D that we know here is a distance of separation between the 2 charges, right? So one, if you just say it's placed along the x-axis, right? So this is minus 9 and here it is a positive 9. So distance of separation between them is nothing but 18 centimeter. So here we know it is a 18 centimeter. So you need to convert it into meter. So when you want to convert it into meter, divide it by 100. So that will give me a 0.18 meter, or else you can also write it to be as a 18 into 10 to the power minus 2 meter, right? So that's the thing that we know here. Straight away go for the calculation. So here 1 upon 4 pi epsilon naught is nothing but 9 into 10 to the power 9. The product of the 2 charges, 7 into 10 to the power minus 6 into minus 2 into 10 to the power minus 6 over the distance of separation is 18 into 10 to the power minus 2, right? Now from here on, students, you can do the calculation work start, right? 9 ones are here, 9 twos are 18, so 2 ones are, and here again 2 ones are, right? So if you just see, this is 10 to the power minus 2, that will get cancelled with minus 6, so here we are left out with minus 4, right? Now what is the final answer that we will be having, right? If you just see here, I'll be left out with a 7 into 10 to the power 9 into 10 to the power minus 6 into 10 to the power minus 4. That will give me again here 7 into, this is minus 6 minus 4 minus 10, and again power is 9 here. That will give me 10 to the power minus 1, right? And here the minus sign we have left out, right? So this minus 2 was there, so that will give me a minus sign here, right? And the final answer that I will be getting is minus 0.7 joule. So that much is the potential energy of these 2 charges, right? Well, now students, let us go for the second part. The second part says how much work is required to separate the 2 charges infinitely away from each other. Right now, the distance of separation is of 18 centimeter. If you want to separate them to infinite distance, right, how much is the work required? Now here, the work that will be required here is nothing but a change in the potential energy, right? So that is going to be a U2 minus final potential energy minus the initial potential energy. What is the final potential energy, right? When the 2 charges at infinity, the potential energy will be a 0. So that is 0 minus of initial potential energy. Just now we have calculated the potential energy between these 2 charges, which is minus 0.7, right? So total work required will be of positive 0.7 joules. So that is the total work requirement to separate the charges to infinity. Well, let us go for the third part, right? If you just see, the third part says, suppose that the same system of charges is now placed in an external electric field. Okay, we are placing them in some external electric field whose electric field is given to be as A, that is some constant, into 1 over r square, where the value of A is given 9 into 10 to the power 5 coulomb a meter minus 2. What would be the electrostatic energy of the configuration B? Okay, so for the first part, we have directly calculated the potential energy between the 2 charges, right? Right now, the potential, we have to find out when it is placed in some external electric field. Now, since we already know the interaction between these two the charges, right? We have calculated the potential, so that will remain the same, right? But addition to that, since we have to find out the potential energy of a charge q1, okay, at that particular point in that external field. Same way for the q2 as well, right? So the very first thing that we have to do, students, we have to find out the the potential, okay, in that space of that due to that external electric field, right? So we know the external electric field is given by this, right? So can we find out a potential, right, equation for a potential? We'll see that, right? So far, students, we know that the electric potential V is nothing but, students, minus integral of the electric field into a dr. This is what we have seen, right, in the previous session. Here, students, if you just see minus integral, right, what is that E? E is nothing but some A constant. I can take it out. Inside the integration, I can see here it will be 1 over r square dr. So this is what we know. Now from here on, students, I can say that minus A, the integration, that r, I can take it on a numerator up, minus 2 into dr. So when you take the integration of r to the power minus 2, so here I'm having a minus A, and integration of r to the minus 2, that will give me, students, r to the power minus 2 plus 1. In the denominator, it will be a minus 2 plus 1, and this is what we have, right? So you just open it up, minus A. So here you can see here in the denominator we'll be having a minus 1. So let me write it here, a minus, and r to the power minus 2 plus 1, that will be r to the power minus 1, and which I can write it to be as 1 over the r, right? So here minus and minus get cancelled. So what is the potential? A upon r. So this is the electric potential we have, right, that we have got it. Now, students, if you just see, let us start calculations of the potential energy now, right? So we know that, students, the total electric potential energy of this two charges, right, when it is placed in some external field, right, it will be, students, the charge q1 that we are having, right, into the electric potential, okay, at that point, at that point where the charge q1 has been placed due to the external electric field, right? So let me write it here, the potential at a point 1 due to the external electric field. Let me write it here, E stands for due to the some external field, right? So that is what I am. Plus, students, I can say the charge q, same way the electric potential at that point 2, okay, due to the some external source we are having, right, the charge source. And students, we already have calculated the potential energy between these two charges. That goes same here, that is a q1 into q2 over 4 pi epsilon naught into the distance d, right? That is the thing we are having here. Now what about q1? Q1, I know it is 7 microcoulomb. Let me write it here, 7 into 10 to the power minus 6 microcoulomb. The potential energy at a point 1, that is, I can use this relation now, right? That is A by R, right? So what is the A? A value already we know, that is 9 into 10 to the power 5, right? And divided by R, right? So what is the R? Let us say here in this case, the R would be, students, 0.09. Let us say if you take this as an origin, okay, here let us consider this is the origin, right? Yeah. So here in this case, that distance, okay, let us say this is the origin of that external source we are having, right? So the distance at which the q1 has been fixed is at minus 9 centimeter. So convert it into meter. So when I convert it into meter, that will be a, students, if you just see, I can say 9 centimeter we are having, right? So that will be, students, you have to divide it by 100, right? So what is going to be? I can say it is going to be a 0.09, it will be a meter, right? So which I can write it to be as 9 into 10 to the power minus 2 meter. So let me write that here, 9 into 10 to the power minus 2 meter. Same way, soon the charge q2 that we are having, that is a minus 2 microcoulomb. So let me write that minus sign here, okay? So let me write it down here, minus 2 microcoulomb, minus 2 into 10 to the power minus 6 into, students, again the A we are having here, 9 into 10 to the power minus it is a positive 5, right, divided by distance of separation. Again it is 9 into 10 to the power minus 2, and this part we have already calculated. The potential energy between the two charges is of minus 0.7 joules. That we have done, right? Now so from here, students, I can say 9 and 9 will get cancelled, right? Same way, students, here 9 and 9 will get cancelled. 10 to the power minus 2, I can say that it will be getting cancelled minus 6 here. So it will be a minus 4. Same way here, 10 to the power minus 2. This is going to be a minus 4, right? Now what is left out, right? So here students, if you just see 7, this is into 10 to the power minus 4 into 10 to the power 5, right? So that will give you a 10, right? Again, minus 2, 10 to the power minus 4 into 10 to the power 5, that will give me again a 10, and minus 0.7. So here 7 tens are 70, minus 2 into 10, that will give me a minus 20, and minus 0.7, so which gives me a 50 minus 0.7, and that will be a student's 49.3 joules. So that's the total potential energy of these two charges when they will be placed in an external electric field. So this is how you do the calculation work. Well, now students, let's go for the third question. Now for this question, students, the charge capital Q, the small charge plus Q and another plus Q here are placed at the vertices of a right angle isosceles triangle as shown below. The net electrostatic energy of the configuration is 0 if the value of Q is dash. So you have to find out the value of a capital Q such that the electrostatic energy is 0. Well, now students, for this question here, it's been told that here we are having an isosceles triangle, right? If you know guys, isosceles triangle, it will be having any two side of it has to be the same. So let us say if this is a side A and this is another side A, right? Yeah. So here in this case, students, the potential energy that we know, that is a capital U, will be 1 upon 4 pi epsilon naught. The charge small q that you are having here, right, into the capital Q, let us say here, right, over the distance of separation between them is going to be, as soon as this is the triangle, so Pythagoras theorem we can apply. This is going to be a square root of 2 times, the A, right? So here I'm having a square root of 2 times the A, plus I can say the charge Q, and here we're having another charge Q, the distance of separation is A, plus I'll consider this charge Q here, and the capital Q over the distance of separation is going to be A, right? So well, now since I know potential energy is 0, here 1 upon 4 pi epsilon naught, I can take it to be some K constant, and from students here I can just take that Q out, okay? Even the A I can take it out. Inside the bracket I will be having Q upon square root of 2, plus it is going to be students, I can say Q, and here again it will be a capital Q. So this is what I'm having. So again it will be a 0 is equal to, students, I can say that it is Q upon square root of 2 plus Q plus capital Q, right? I can take that Q, the small q, on the left side, and when I take it on the left hand side it will become minus Q. So here it will be a Q, okay, and inside the bracket I can say 1 upon square root of 2 plus 1, right? And I can say that minus Q will be equal to capital Q, and I can just solve this. It will become 1 plus square root of 2 divided by, it is going to be a square root of 2. I'm interested in a Q. So what will be the capital Q? Capital Q will be a minus Q, right? Or as while writing here minus square root of 2 times the Q over the students, I can say it is a 1 plus square root of 2, right? So this is what the Q that we are interested in, where the, the electrostatic energy is going to be a 0. Now here in this today's session, we have discussed the term electric potential energy for a system of point charges, which is nothing but the amount of work done in assembling those point charges at their locations while bringing them in from the infinity, right? Then later we have also obtained the equation of a potential energy for a system of charges, and this is a student's equation to find out a potential energy when you will be having n number of point charges in your chosen system. Then later we have also obtained the equation for a potential energy when the charges will be placing in some external field, and over there, students, we have discussed by taking the two charges Q1 and Q2 placing in that external field, and here this is the equation that we had obtained, right? And then later we have also obtained the the electric potential energy for a dipole placing in an external field, and here if you just see the relation here, students, it will be a dipole moment into electric field cos of theta 1 minus cos of theta 2. Theta 1 here is the initial angle at which you are placing the dipole with the the electric field, or else it's the angle between the dipole moment and the electric field, that's the initially, and theta 2 is your final angle, right? So if I place my the dipole perpendicular to the electric field, in that case theta 1 will become 90 degree. So theta of 90 cos of 90 is going to be a 0, and theta 2 I can replace it by theta. So here I'm also having another relation, that is minus dipole moment electric field into cos of theta, where theta is angle between the dipole moment and the electric field. So students, these are the equations which you're going to make a note. And students, this is all for this today's session. See you guys in the next session. Till then, keep learning. Bye bye.